Hi and welcome to this Leaving Cert Higher Level Maths Revision video where we're going to look at a Section B question on trigonometry and calculus. Part A of this question tells us the diagram shows a right circular cone with a fixed slant height of L centimeters. The slant height makes an angle of theta with the vertical, where theta is between 0 and pi over 2. So we're working in radians. Remember, your pi is 180 degrees, so pi over 2 is our 90 degrees. Part I then asks us to express the radius and height of the cone in terms of L and theta, and hence show that the volume of the cone is pi L cubed over 6 times sine theta sine 2 theta. So let's just pull out that triangle to work with it. We have a theta here and an L here. We would have a radius, which would be this one, and h, the perpendicular height, would be there. So as a right angle triangle, we're going to just use our sine, cos and tan. Here's my hypotenuse, here is my opposite, here is my adjacent. So when we're working with this, we're going to work with one ratio that has or and one ratio that has h. So sine of theta is opposite over hypotenuse, so or over L. So or is equal to L sine theta. If we want to work with the h, which is adjacent, we're going to work with cos. So cos theta is adjacent over hypotenuse. So h is equal to L cos theta. So that's our first part done, expressing the radius and height of the cone in terms of L and theta. So now let's get the volume. So I'm going to use my log tables, which gives me the formula volume of a cone, and I'm going to use what I've worked out for or and what I've worked out for h. So the volume is equal to 1/3 pi or squared, which is L sine theta squared, times h, which is L cos theta. So if we're working kind of looking at what I want, the pi is there. The L cubed is there because I can pull this L squared out times an L, which gives me L cubed. Now it is over a 3 and not a 6, so we'll have to see what happens there. And then I get sine squared theta cos theta. So my trigonometric piece is a little bit different. I have a sine squared theta cos theta. Here is a sine theta sine 2 theta. So I suppose let's pull out the piece that we do have and we're kind of happy with, which is just a sine theta. And then that leaves me with a sine theta cos theta. So is there something in the log tables that will help me work with this? So on page 14 of my log tables, I have a little identity that is sine 2a is equal to 2 sine a cos a. Now the only difference is there's a 2 in front of it. So if I wanted to put a 2 here, I could balance it out by putting a 2 underneath the line. So effectively, because all of these pieces are multiplied together, those 2's will cancel each other out. They would divide into each other to give 1. And now I can use my identity. So this tidies up into pi L cubed over 6, which is what I wanted. My sine theta is still there, but now this 2 sine theta cos theta actually changes to sine 2 theta, which is exactly what they have asked for in this part of the question. So this is a great example of how identities can be brought in to a question. Part 2 then asks us to find a value for theta for which the volume of cone is a maximum. Give your answer in the form tan inverse of root 8. Now don't worry too much about the form they want the answer in. Focus first on the question. So it's talking about maximum. So anytime we want minimum or maximum, we're going to have to use differentiation. So let's look at our derivatives here. And we're working with this formula here. So the volume is equal to pi L cubed over 6 sine theta sine 2 theta. Now this is the product rule. You can work with this a few different ways. What I'm going to do is split it out as my u is pi L cubed over 6 sine theta and my v sine 2 theta. Because remember, again, all of these pieces are just multiplied together. What you need to remember for our product rule is that you split out the two things we want to differentiate. So we want to do dv d theta. So as long as each piece has a theta and only one theta, then we're fine. So let's differentiate du d theta. This whole piece here, that is effectively a constant. Now I know L technically is a variable, but for us trying to differentiate it, we're differentiating with respect to theta. So this is treated just like a normal number in front. So sine theta, if we look over on the left hand side, goes to cos theta. So we get pi L cubed 6, and this is cos theta. dv d theta sine 2 theta goes to cos theta, but this is the chain rule, sorry, cos 2 theta, but this is the chain rule. Because of that 2 in front, we have to multiply by the derivative of that inner function, and the derivative of 2 theta is simply 2, so we end up with this. So putting it back together to get now capital V, I know we've two V's going, this is little v. So this is our capital V. So we're going to do dv, big V for volume, d theta, we get u pi L cubed over 6 sine theta times dv d theta, which is 2 cos 2 theta, plus v, which is sine 2 theta, times du d theta, pi L cubed over 6 cos theta. So what we can do is actually pull this and this out to the front because it is a common factor. It's in both terms. In this case, we do have two terms because they're separated by a plus. So if we pull that out in front, what we're left with looks like this. So pi L cubed over 6 times 2 sine theta cos 2 theta plus sine 2 theta cos theta. Now we're trying to find the value of theta for which the volume is a maximum. So to get the maximum, we let the first derivative, or in this case dv d theta, equals 0. So we get pi L cubed over 6 times 2 sine theta cos 2 theta plus sine 2 theta cos theta, and let that equal to 0. Now we can divide across by what we've pulled out in front. So if we divide across by pi L cubed over 6, we end up getting rid of it because 0 divided by anything is still 0. And we're simply left with 2 sine theta cos 2 theta plus sine 2 theta cos theta equals 0. Now you can keep them all on this side or you can bring it over to the other side. I think maybe it will be easier to see if we move things across. So I'm going to move over the first term, so this whole piece. So I'm left with sine 2 theta cos theta equals minus 2 sine theta cos 2 theta. And I need to solve for theta. Now, a hint, and we can start looking at this now, is that the form they want it in is a tan. So if I look at what I have, sine divided by cos will give me tan. So if I divide this side by cos theta, which makes this a tan theta, and this by a cos 2 theta, which effectively cancels this piece out, and I do it to the other side as well, so cos 2 theta, I'll just write them the other way around. Remember, multiplication order doesn't matter. And what I end up with is here sine divided by cos, again a tan, and cos over cos, which is a 1. So we end up with a much simpler sine 2 theta over cos 2 theta tan 2 theta is equal to minus 2 sine theta over cos theta, and that is tan theta. So that's what we have. We're trying to work out theta, but at the moment we've too much going on, so we need to look for something that we can change that tan 2 theta to just theta. So we go to our log tables and look on the identities pages. So I'm going to go to my log tables, page 14, and I have this identity here that will help me. So tan of 2a is equal to 2 tan a over 1 minus tan squared a. So in terms of theta, that becomes 2 tan theta over 1 minus tan squared theta is equal to minus 2 tan theta. Now you can keep working like this, or if you want to simplify it, if you struggle working with those trigonometric identities, because they're quite confusing to work with tan, sine, cos, because they're words, we can let x equal tan theta, so using a substitution. The reason we can do that here is because all of these can be written in terms of tan. So I have 2x, 1 minus x squared equals minus 2x. Can get rid of the fraction, multiplying both sides by the denominator. I get 2x equal to minus 2x times 1 minus x squared. I can divide across by 2x to make this a little bit simpler. And 2x divided by 2x gives me 1 minus 1 plus x squared. I then get x squared is equal to 2. So x is equal to plus or minus root 2. Now, remember, this is actually tan of theta is equal to plus or minus root 2. So we've actually got two answers, but they only ask for one value. So if we go back and think about our unit circle here for a second, C-A-S-T. So are we talking about which quadrant? So if I look at the start of the question, they told us we were only working in that first quadrant. So that first quadrant has to be positive, meaning my answer for tan theta is just a root 2. And then writing it in the form that they want is tan inverse root 2, which is exactly the way that they wanted it. So part 3 asks us to find the maximum volume of the cone. Give your answer in third form and in terms of L. Now that third form is going to make life a little bit more challenging, because if it was in a decimal form we could just go straight to the calculator. We're going to have to do a bit more work here. So I have my volume. I also have the theta, which maximizes that volume. So all I need to do is to sub that theta into that formula. But to keep it in third form, I'm going to need to be a little bit clever about this. So let's go back to our theta, and this can be written as well, tan theta is equal to root 2, and I could write that as root 2 over 1. I can then use a little right angle triangle, whatever kind of triangle I want, to try and figure out sine and cos. So I'm going to put my theta here. Here is my opposite, here is my hypotenuse, here is my adjacent. If I'm working with tan, I'm opposite over adjacent. So this is opposite root 2, adjacent 1, using Pythagoras. So C-A-B, I have C squared equals A squared plus B squared. So I have c squared is equal to root 2 squared plus 1 squared. So that's 2 and 1 is 3. So I get c squared is equal to 3. So c is equal to root 3. And that allows me to write sine of theta as opposite root 2 over hypotenuse root 3. Now, I also need a sine to theta, so I'm going to go back to my log tables to look for that. So my log tables, I have what I used in part I, so sine of 2a is equal to 2 sine a cos a. So if I work out cos theta, it's adjacent over hypotenuse. So therefore I can work out sine 2 theta, which is 2 sine theta, which is root 2 over root 3, cos theta 1 over root 3, and that gives me 2 root 2 over 3 for my sine 2 theta. And now I can take my sine theta and my sine 2 theta and sub it into my volume formula. So my volume is equal to pi L cubed over 6. That's all fine because it needs to be in terms of L. Pi is a number and 6 is also a number. So we sine a theta, so that's root 2 over root 3 times sine 2 theta, which is 2 root 2 over 3. So we want to try and simplify this as best we can. So root 2 by root 2 is 2. So I get 4 pi L cubed on the top line, and then I get 18 root 3 on the bottom. I can simplify by dividing 2 into the top and into the bottom. So I end up with 9 root 3, and that's my volume. So part B is a follow-on. We still have an inverted cone, but the question differs slightly. So it says a water tower is an elevated structure which supports a water tank constructed at sufficient height to pressure a water supply system for distribution of drinking water. It also serves as a reservoir to help with water needs during peak usage times. The water level in a tower typically falls during daytime usage, and then a pump fills it back up during the night. The reservoir tank in the tower is in the shape of an inverted right cone as shown in the diagram. The slant height of the cone is L, and it makes an angle of 45 degrees with the vertical. During daytime usage, it is observed that the rate at which the water level drops in meters per hour is given by dx dt is equal to root 2, where x is the fall in slant height in meters from the maximum capacity, which means volume of the tank, and t is the time in hours from the instant that the water level begins to fall from this point. Find the capacity of the reservoir when it's full. Give your answer in third form and in terms of L. So this word capacity means the same thing as volume, but we tend to talk about the capacity of a vessel, so something that holds a liquid, and the volume then the liquid inside of it. So that we would talk about the volume of water, but the capacity of the water tank. But pretty much from a mathematical point of view, the calculation is going to be the same. So let's pull out this little right triangle. I have my slant height L, 45 degrees, and we want the capacity, so our volume. So our volume is 1/3 pi r squared h. Now, we only want this in terms of L, but I need an r. So here is the radius r. So I'm going to write my r in terms of L using that 45 degrees. So this is my opposite and my hypotenuse. So I have the sine of 45 degrees is equal to r over L. So r is equal to L sine 45, which is 1 over root 2. So that's L over root 2. Or if you're using your calculator, it will be root 2 L over 2. So my volume then is 1/3 pi r squared. So I'm going to use L over root 2. If you use the other, it will still give you the same answer. That's squared. And the height. So now I also need the height in terms of my L, and I can work that out over here as it's my adjacent. So a very similar method to what we had been working with. So cos of 45 degrees is equal to h over L. So h is equal to L cos 45 degrees. So h is equal to L over root 2, or if you're using your calculator rather than page 13 to get this, it will be root 2L over 2. So I'm going to write this again as L over root 2. Now, what I suppose my diagram doesn't show it very well, but if the angle is 45 degrees, this would have to be an isosceles triangle. So OR and H would have to be the same. So if you figured that out, you wouldn't have had to go back and use cos. You could have just used that one answer, knowing that OR is equal to H. So tidying this up, I get pi L cubed over 3 by 2 by root 2, so don't forget your squaring here, which simplifies to pi L cubed 6 root 2. If you did use what the calculators gave, so that root 2 over 2, make sure to check that you can simplify, or check that you have simplified that fraction at the end. So if it looks different, it will be because there is a fraction that can be simplified. Part 2 then says, hence show that the volume of water in the reservoir tank at time t is pi over 6 root 2 L minus x, all to be cubed. So we're going to go back and use this triangle, but actually there's a smaller one when there is an x, because x is how much it's decreased. So I still have my 45 degrees here, but then this length here is now L, take away that X. So again, it is still, despite my diagram not looking like it, it is still an isosceles triangle. So even if we just work out our OR using the exact same method, so my opposite, my hypotenuse, my adjacent. So sine of 45 degrees is equal to OR over L minus X. So sine of 45 is 1 over root 2, or root 2 over 2 if you're using your calculator, L minus x. And that gives me L minus x over root 2 equals my radius. But again, also my height because of that isosceles triangle. Our volume is 1/3 pi or squared, so L minus x over root 2 squared times h. L minus x over root 2. So I end up with V is equal to pi times L minus x, all to be cubed. No need to multiply them out. And I get a 3 root 2 squared times root 2. Root 2 squared is 2. 2 times 3 is 6. So I get pi over 6 root 2 L minus x cubed. So that's exactly what they've asked us for. So part 3 then says, find in terms of L and T the rate at which the volume in the reservoir tank is decreasing with respect to time. So the rate at which the volume, so that is dV dt. Now, we have been working with V, but there's no T in it. There's an X, so I can work out dV dx. But in order to then get dV dt, I'd have to multiply this by dx dt, which luckily we have been given here in the question. So first thing I'm going to do is I'm going to take my V and work out my dV dx. So here is my V. So dV dx, I'm going to use the chain rule. So bring down the power and then take one away from the power and then multiply it by the derivative of the inner function. So my inner function, because I'm doing it with respect to x, is this. Remember that L represents a number in this case because we're differentiating with respect to x, which means that this breaks down to a -1. So a derivative of L minus x will just be a -1. Simplifying that, I get minus pi over 2 root 2 L minus x, all to be squared, and that is my dV dx. And notice how the question it asks, find in terms of L and T. We have in terms of x, so we need to do a bit more work on that, but it did say that it was decreasing with respect to time. I have a negative dV dx, which means that that is a decreasing. So I need to now figure out, how do I change my x to a t? And the answer is to use this little piece here. So we have dx dt, and if we integrate that, we can bring it back to x is equal to square root 2t plus c, so the constant of integration. Now, they told us something in the question and it mightn't have stuck out, but x is the fall in slant height in meters from the maximum capacity of the tank, and t is the time in hours from the instant that the water level falls from this point. So that is telling us, in maybe not the most explicit way, but that when t is equal to 0, x, the drop, is equal to 0. So time starts counting when the tank is full. So working those through, we end up with c equals 0, which means that x is simply root 2t. So I can go back to my dv dx and change that. So dv dx and get minus pi over 2 root 2 L minus root 2t, all to be squared. And then going back over here, all I need to do to get my dv dt is to take that and multiply it by, hopefully I have enough space here, minus root 2t squared, multiply it by dx dt, which is root 2. This root 2, because effectively it's like a root 2 over 1. So the root 2 on the top here will cancel with that bottom and it cleans up nicely. So our final answer then for dv dt is minus pi over 2 L minus root 2t, all to be squared, which is, if we double check with our question, this was quite a long one, find in terms of L and T. Yeah, we have that, the rate at which the volume of the water, so dv dt, is decreasing, and our final answer was a negative, which we were expecting since dv dx was negative. So the final part of this question asks us to find the rate at which the volume of the water in the reservoir tank is decreasing with respect to time. So that is finding our dv dt when it's 1/8 of the capacity is remaining. So we need to figure out when that happens. When is there 1/8 of the capacity remaining? So the original capacity, so when it's full, which we did in part I of, so BI, was given by this. So I've written this as V0. So let's get 1/8 of the original capacity. So let's do 1/8 of this. So 6 root 2 L to the power of 3, which ends up as pi L cubed all over 48 root 2. Now, we know that the volume at any time can be written like this. Now, I know that what the volume will be, so I can now equate what I've just worked out, this capacity, against this capacity to figure out x, so how far down, or the reduction in slant height, which will in turn help us find a t. So I'm going to let pi L cubed over 48 root 2 equal to pi 6 root 2 L minus x cubed. So there's a root 2 on both sides underneath the line. There's a pi above the line. 6 goes into 48 8 times. So simplifying this gives me L cubed over 8 is equal to L minus x all to be cubed. So I'm going to break this fraction up by multiplying both sides by 8. And we have something that looks very, very complicated. However, 8 is also a cubed number. So I could write this as 2 cubed, and then I have L minus x cubed. Because if I do that, I can actually cube root both sides, which will give me L is equal to 2 times L minus x, which simplifies this question so much. So I have L is equal to 2L minus 2x, which gives me 2x is equal to L, so x is equal to L over 2. Now, remember that we worked out in the last part that x was equal to root 2t. So I have root 2t is equal to L over 2. Dividing both sides by root 2, I get t is equal to L over 2 root 2. So now I know the time when the capacity is 1/8, or when the volume of the water is 1/8 of the capacity. And now I can go back to my dv dt and simply sub it in. So I have dv dt is equal to minus pi over 2 L minus root 2 L 2 root 2. And this is all to be squared. Those root 2's cancel, making that L minus L over 2, which is simply 1 take away a half, which will leave me a half, or in this case L over 2 squared. So that's minus pi over 2 times L squared over 4, which gives me minus pi L squared all over 8. And that is the rate at which the volume in the reservoir tank is decreasing with respect to time when 1/8 of the capacity is remaining.